So today we'll talk about benchmarking and how you're doing wrong. And these are some of the things I've also done wrong. So a little bit about myself. I'm Aysylu Greenberg. I work at Google on distributed build systems. And I'm also a maintainer of the open source library called Loom, which is a graph algorithms and visualization library written in Clojure. There's the right way and the wrong way to do benchmarks. So let's get started with a simple case. Stopwatches. In order to write benchmarks, one needs to be full stack. So one needs to understand the front end and the back end of the system, as well as the bytecode and the internal representation emitted by the compiler of the language, and the low-level code, machine code generated by the code generator, as well as the operating system, the hardware, all the way down to the gate level, and the device physics if you have to. And let's not forget about the network layer and our users. How our users utilizing our applications, what code paths they take is incredibly important before we set up benchmarks. But not everyone has access to this knowledge, partially because it takes a lot of very focused effort to acquire such knowledge in the first place. And part of it is because some of that knowledge may not be available to us. We treat a lot of parts of our systems as a black box. How many of you actually know how your processor works, like all the implementation details of the processor? Probably not many of us, unless you work at that company who builds the processor, because a lot of it is behind intellectual property. But that doesn't mean that we aren't able to write better benchmarks. So let's discuss how we can do that. So in this talk, we'll specifically focus on benchmarks that measure how fast your program runs. Of course, there are also quality benchmarks, but quality is something that is different depending on the context. So it's very hard to quantify it because you'll have your own definition of quality, and I have my own definition of quality in my application. So today we'll focus specifically on measuring runtime. So in business, benchmarks is when you compare your process to a goal, or when you compare your process to industry's best practices. So why does the business definition matter in this case? Well, because when we set up benchmarks, we do not only focus on performance, but also on what the performance goal is. How fast is fast enough so that your users are happy and your bills on the infrastructure are kept low? So today the talk will be in 3 parts. First, we'll talk about how not to write benchmarks. Then we'll talk about different pitfalls, common pitfalls that occur when setting up benchmarks and interpreting results. Specifically, we'll focus on how you're wrong about machines, you're wrong about stats, and you're wrong about what matters. And then in the end, we'll discuss what tools we have and what kinds of things we can do in order to avoid such pitfalls. In this talk, I will not be naming many different products, but these are very much real-life examples. But we'll focus on the concepts. So how not to write benchmarks? Let's discuss a contrived example of a benchmark. You'll probably find many issues immediately with it, but we'll use that as a starting point. So we have a website serving images. So a web request comes into the server, and the server has an option of serving it either from the cache server or from S3, so some cloud storage. And we'll do this in a way that we'll access one image 1,000 times. We'll measure latency for each access. We'll start measuring immediately as soon as our application starts up. We'll do 3 runs, and we'll take the mean. And we'll do this in our dev environment because our production cluster is busy churning through the production workload. The reason we would like to measure how long it takes for us to retrieve images is because images are slowest to load, so that sounds like a good thing to measure. So what's wrong with this benchmark? Well, there are many things that are wrong with this benchmark, so let's take it apart one step at a time. When it comes to machines, you know nothing, Jon Snow. Caches are everywhere in all the different layers of our applications. And it seems that our favorite way to solve our latency problem is just put a cache on it. And it's actually caches all the way down. And most caches are structured in a hierarchy. So at any given point in time, only one cache will be serving the requests. So in our example, whenever a web request comes in to retrieve the image, the server has the option of either retrieving it from memory or from the cache server or from the cloud storage. So let's look at caches in processors in greater detail. So we have, for each core, we'll have actually 2 level 1 caches for instruction cache and data cache. And we'll have L2 cache for both instruction and data. And then we'll have L3 cache shared across multiple cores, in this case, 4 cores. And what you see here is inclusive cache policy. What that means is that in level 3 cache, you'll have data that is also in level 2 and level 1 cache, as opposed to exclusive, where they will not be sharing. So higher level you go, it will not contain the data that is in lower levels. Okay, so now for level 1 cache, in this particular case, it's 32 kilobytes. So if we have 4,000 in 32s, so 32-bit integers, then 4,000 of them will fit into L1 cache, 4,000 unique of them. And there are different costs associated with accessing different levels of cache. So in order to access L1 cache, it would only take a half a nanosecond. To access L2 cache, it would be 7 nanoseconds. And to access L3 main memory, it would be 100 nanoseconds. Okay, so now not always are our caches structured in a hierarchy when it comes to reasoning about a system. For instance, if you have a bloated binary, so if your clients can take many different code paths through your system, so when you try to cache them, next time the client takes a new path, it will be completely different, so you will be missing instruction cache. So in this case, the bloated binary will be hurting performance because instructions will keep missing the instruction cache. So no matter how much you tune your memcache server, you won't get any benefits because the bottleneck is in instruction cache. So understanding what architecture of your caches are that you're interested in measuring is very important. So for most benchmarks, it's important to remember that you're benchmarking one particular cache level. Let's talk briefly about prefetching. Who here is familiar with what prefetching is? Specifically, I'm talking about hardware prefetching. Okay, so this will be fun to talk about. So what we have here is we have an array A of size n, and what we'll do is we'll iterate through all the elements in the array and increment the value in that array by 1. And we'll do this repetition number of times. So if we were to disable prefetching or run this program on earlier processors before hardware prefetching was implemented, what we'll see is something like this. So on the x-axis, you see n, which is number of elements in the array, and then y-axis is the latency, the lower the better. And you see very distinct 3 steps where access time is actually governed by which cache level you're accessing. And now on later processors, more modern processors where hardware prefetching is available or you can enable it, you will see is that no matter what the size of the array is, the access time will be the same. How does that happen? That happens because your hardware is able to detect memory access patterns. In this case, you're just iterating over every element. So it's able to hide the latency by prefetching the memory for you before you even need it. And thus, it's able to make it appear like it's the same as accessing it the previous times. Okay, so now we would like to defeat our prefetcher, and what we'll do is we'll set up the following program. So instead of accessing every single element in a row, we'll do some pseudo-random number generator, and we'll defeat the prefetcher, so it won't be able to guess what memory access we'll access next. And now we would like to know how long does it take for us to iterate over elements. So now again, on the x-axis, we have n is the number of elements in the cache, in the array, and then y-axis is the latency. The lower, the better. And what we see here is 4 distinct regimes that our program goes in. So these are the 4 different regimes. And on the y-axis, on the right axis, which is not marked here, what we actually have is we have cache misses. So what we find is that for up to 32,000 elements in the array, our performance is dominated by L1 cache effects. All of the data fits into L1 cache. Now for between 32,000 and 128,000, we'll start missing L1 cache, and now it's dominated by L2 cache access times. Now, when we have over 8 million elements, the performance will be dominated by L3 cache effects. And the small artifact you see in between is actually due to translation loci buffer misses. So it's important to remember here that we're accessing one particular cache level depending on the size of data that we have. So in this case, accessing one image 1,000 times is simply not enough. So what's a better way to go about this? Well, we need to know what the goal of the benchmark is. That depends on what we want to know. If we're interested in a realistic distribution, for instance, our users are accessing 90% of the time top 5 images and 10% of the time the rest of the random images, then we would like to have our distribution to be modeled like that. If we're interested in the access time to cache, then we want to make sure that we access images that are stored in the cache. So we'll first make sure to fill it up in the cache, and then we will access those. And if we're interested in access time to the storage, to the cloud storage, then we'll make sure that we don't access the same image twice so that it can be cached. Okay, so now let's talk about warm-up and timing. If you're writing in a JVM language like Clojure, Java, Scala, then your program will execute in 3 different modes. First, it will be executed in interpreted mode, where the bytecode instructions will be executed one at a time. And then the JVM will actually figure out which instructions, which functions are executed most, and will compile them. So your program will execute in a combined mode. Afterwards, most, if not all, of the program will be compiled, and you'll be running in a more or less steady state. Another example of warm-ups is cache filling. So when you start up your application, it takes time for the application to figure out what is the data that you access most frequently. So warm-up is the cost that you pay once in a long-running application. So when you run, your benchmark matters significantly. If you're interested in the performance of a steady state application, then warm-up time is something that you'd like to exclude and not include in your results. And if you're interested in the failover behavior, then warm-up time is exactly the thing you're interested in measuring, because you want to know how long it takes to bring up a new service once your previous service went down. So in this case, measuring latency, it will skew our results to the high latency side. So it shouldn't be part of the benchmark because we're interested in the steady state performance of the application. Now let's talk about periodic interference. It happens when you have constructive and destructive interference due to periodic processes. What we see here is a snapshot of a heap taken with JVisual VM. So x-axis is just time as it goes by, and then y-axis is the size of the heap. So orange line shows you the allocated amount of heap that you can use, and the blue line is the used heap. And the peaks that you see and the dips are actually the GC pauses, the garbage collection pauses. So the red dotted line shows you when garbage collection happens. So if you were to measure the duration of active requests during the garbage collection process, you would see that requests take much longer to complete than if you were to measure it in any other times. Similarly, if you want to measure number of concurrent requests happening during an indexing operation, you're guaranteed to see much lower number than if you were to measure not during the indexing operation. So in this case, if we measure that right during the garbage collection, and then every single other measurement is also coincides with garbage collection pauses, then we are guaranteed to see that requests are taking longer. And if they're not exactly synced, so if we measure during garbage collection pause, and then next time right before it, and then next time right after garbage collection pause, and so on, then it will look like our measurements don't really make much sense. They're all over the place, and it will be hard for us to figure out how long our requests actually take. So in this case, measuring latency for each access is not really beneficial for us. What we'd like to know is both latency and throughput, because it will tell us whether we're synchronizing with one of the periodic processes. Also, it can help us figure out if we're dealing with coordinated mission, which we'll talk about in a few minutes. Now, another common pitfall, which may not always be a problem, is running your benchmark in a test environment or dev environment, which is different than your production environment. If you're interested in just figuring out which function takes most time, so if some function takes 90% of the time, then it's possible that it's most likely that in both test and production environments, they will take about 90% of the time, majority of the time. Now, if you're interested in more subtle effects, you might observe different cache effects due to bigger RAM and different compute powers available to you. So you should try to match up environment as closely as possible, unless you're absolutely sure that the differences in the environments will not affect what you're measuring. So the rule of thumb is you would like to try to compare apples to apples. So try to make sure that the things that are different do not affect your measurements. So in this case, using dev environment may not be good for us because maybe on my laptop, I don't have as much RAM as I have on the production machine, so I'm going to be measuring different cache effects. Now, a much more subtle thing that is commonly dismissed is power mode changes. You may be familiar with dynamic frequency scaling or CPU throttling. Intel has a technology implemented called speed step that does that. So like your processor may run on 1 gigahertz, then power up to run at 4 gigahertz, and then go down to 2 gigahertz. On a Linux machine, you can actually figure it out by looking at the scaling governor. And it will tell you whether it's on demand, which means you're actually doing CPU throttling, or performance, which means that it runs at 100%. And you can get what the current CPU frequency is set to run at by looking at the CPU info. OK, so now let's talk about stats. Stats are hard to get right. So one of the most common pitfalls when doing benchmarks is taking too few samples. Too few samples just don't give you enough data. And you may also have outliers in that data, in which case you can't really reason what the distribution of the measurements that you got are. So how many runs is enough? There's one way to figure this out, which is you may want to use convergence of medians. So on this plot, what we see is x-axis is time, and y-axis is latency. And there are two different applications. So let's focus first on the top half of the plot. So blue dots are samples that we measured, and red dots are the medians. So now median is pretty noisy at the beginning, but towards run 10, it starts more or less converging. And then towards time 20 and definitely 40, it's more or less converged. So maybe in this case, 20 or 40 runs is sufficient for us. Now, on the bottom part of the graph, purple dots are the medians, and the green dots are the samples. So what we see here is that at time 3, our latency drops to 22, say, milliseconds, if that's our units. And then it goes up to 40, and it goes a little crazy at the beginning, but then towards time 40, it starts converging over time and stabilizing. So maybe 40, maybe 80 runs will be sufficient in this case. And unfortunately, sometimes you may discover that your application doesn't actually stabilize at all. So it also, for how long you run your benchmark, or how many runs you take, also depends on whether you're interested in exploring the long tail. If you're interested in exploring a long tail, make sure that you measure it for much longer. So some of the systems I worked on, we were interested in artifacts that would see days after the system was started up. So we were interested in running it like on a week-long scale to see if any of that happens that we wanted to get rid of. Okay. So in this case, doing 3 runs is just simply not enough, because if we have one outlier, then we have just 2 other results that are more or less within our distribution, but we don't really know what it's like. Now, normally you have a normal distribution. So when you have a normal distribution, your mean and standard deviation will be enough for you to reason about your data. It will tell you everything you need to know. But due to complexity of systems and different parts of systems that we measure in different effects, you may not have a Gaussian distribution. And in that case, mean will not be a must. It will not be sufficient. Mean is also known as average. So if you have 10 requests that take 1 millisecond, and one request that takes 10 milliseconds, then our mean average would tell us that the request took 2 milliseconds. Now, median, on the other hand, will take this data, sort it out, and then take the middle point, which will tell us it takes 1 millisecond, which is much better representative of this data. Similarly, percentiles show us distribution and are much more robust in the presence of outliers compared to standard deviation. So in this case, finding mean may not really give us the data. We always may have outliers, with the 3 runs, and then getting the average could be very misleading to us. You may also not be dealing with single mode distributions. So why do we talk about means, medians? Like often we talk about 50th percentile, 90th, maybe 95th, 99th percentiles, and then we get more sophisticated with extra nines. So why do we pick particular points? Well, we want to summarize data so we can talk about succinctly. Otherwise, we would have to just present the raw data, which is not really helpful to anyone. So the problem with 50th percentile, though, is that all it tells you is that half of the time you're doing better and half of the time you're doing worse. So half of the time you're faster and half of the time you're slower, which is not really that helpful. And it could be completely useless if you have multimodal distribution. So imagine the following scenario. We have x-axis is latency, measured in milliseconds here, and y-axis is the number of occurrences. So now what we have here is that 50th percentile is measured in more occurrences than the 99th. So 4 milliseconds occur much more frequently than 10 millisecond latency. Okay, so far so good. So imagine what this distribution looks like. Well, this is what it actually looks like. So in this case, 50th and 99th percentile don't really tell you much about what you measure most frequently. In this case, maybe 25th and 75th percentiles would give you better estimation of your data. So make sure to always look at histograms, because they will tell you what the distribution is, what the modality of your distribution is. There's also another way to do this algorithmically. There is a Silverman's multimodal distribution detection algorithm. So it gives you an algorithm to run on data to figure out if it's multimodal and how many modes it has. For those of us who are less sophisticated with statistical knowledge, which this paper is very, very complicated, there is a fantastic blog post by Matt Adareth that talks about, that gives intuition into how this works. Now, my favorite topic is outliers. Unfortunately, outliers don't get the attention that they really deserve when reasoning about data, when interpreting our data sets. They also allow us to detect whether coordinated emission happens. So let's talk about that, since I promised that. So imagine the following scenario. We have x-axis, just one axis time. Say we measured in milliseconds. And we have a client that sends requests to the server. And it would send requests every 10 milliseconds. And usually our server responds within 1 millisecond. So sending every 10 milliseconds sounds reasonable to us. So we'll send a request at 0 milliseconds, get a request at 1. Send a request at 10, get a response at 11. Now send another request at 20. And now the server goes into a garbage collection, network partition happens, you don't hear back from the server until time 69. And then we send the request at 70. And now everything goes as expected, so we hear back from the server at 71, send the request at 80, and so on. So now when we get our data, we see that one request took 49 seconds. And this looks like an outlier because everything else took 1 millisecond. So we just toss it out and we forget about it. And now we think that most of the time our data, our response comes back to us within 1 millisecond. So what happened here? Here we coordinated with the server, the client coordinated with the server by waiting for it before sending next request. And we omitted some data. So in those 20 through 70 seconds, we could have sent 4 more requests, but we didn't. So we're missing some data. In fact, we'll measure that our latency median will be 1 millisecond, and our mean will be about 11 milliseconds, which is not really what we are seeing here. But that's the data we will get after we measure it. And we see that 44% requests didn't complete. So instead of throughput being 100 requests per second, we only got 60 requests per second. So in this case, having basic loops that work for measuring, so basic loops don't really work well for measuring stats of each request. So you need to do something different. You want your client to be sending no matter whether you heard back or not, and measure that. There is a fantastic talk by Gil Tenney called How Not to Measure Latency that goes into much more detail on coordinated emission. So I highly recommend watching that. And it goes into much more detail than I will go in this talk. So another thing about Outliers is that it reveals to you whether you're missing SLAs. SLAs are service level agreements, so basically a contract between you and the user of the services for delivery times. Another thing that Outliers help you with is detect whether something will be a problem at scale. So if something happens 1% of the time, so 1 out of 100 times, and suppose that your web server actually on the page loads 100 images, and one image takes 10 times as long, you're guaranteed that every single user that will hit that bad latency and will be delayed by 10 times. So when you work at scale, just statistically, you will see that things happen much more often because there are many more events that you'll be encountering. Now let's talk about something that, or some real story that helped us, how Outliers helped us find lots of bugs. So I'm going to be very vague about very exact things, but I worked on setting up a performance analysis pipeline for search infrastructure back when I worked on a search engine. And basically the way system was set up in rough details is a URL would come in into system A, then it go through system B and system C, so you have a nice pipeline. Okay, so now what we measured is this heat map, where the colors, the darker the color, the fewer URLs were measured for that particular latency. And then now x-axis is the time it took for the URL to get from system A to system B. And the y-axis is the time it took for the URL to get from system A to system C through system B. Okay? So now ignore the bottom part, the bottom dark blue part. That's not really interesting to us. But let's focus on the top part, and specifically the top right corner. Briefly, in the bottom left corner, what we see is some clustering of URLs, and then it starts fading away until we get to the top right corner, which looks suspicious. Those URLs didn't make up high percentage, and we were about to ignore them until we started looking into them. So as I was looking into them, what I was able to detect is multiple issues with how our benchmark was reasoning about our data, how it was interpreting our URLs, and also multiple bugs in our production software. So once I fixed some of those bugs, I got something like this. So we were able to get rid of some URLs because they didn't fit into this data set. And so we see some of, there's fewer URLs, more clustering happens towards the bottom of the graph, and there's still some clustering on the top part. Again, those URLs made up a very tiny fraction of all the URLs that we were measuring, but we continued looking into them. And as we looked into them, we actually discovered that there was some time component associated with 75 time units, which is, starts out somewhere there, which is where the clustering starts out. And we were making a lot of assumptions based on that time component. So once we fixed that, we got something like this, where now this data was actually confirmed by several other different analyses that we ran on the data. So it confirmed to us that this was a correct way for us to represent our data to get results of our benchmark. And now we don't see anything related to the 75 time unit component that we got previously. So Outliers have been tremendously helpful to us in finding numerous bugs in both the benchmarks and the production software as well. So now let's talk about how you're wrong about what matters. Many different people who write the favorite part of the software are very excited to make sure that that's not the bottleneck. So they'll go ahead and try to optimize it enthusiastically. And I couldn't have put it better myself than Donald Knuth. So let's see what he says. He says that programmers waste enormous amounts of time thinking about the speed of non-critical parts of their program. We should forget about small efficiencies 97% of the time, as premature optimization is the root of all evil. Yet we should not pass up our opportunities in that critical 3%. Often, even most seasoned programmers can't quite predict where the bottleneck will be. So jumping on to optimizing your software, your part of the system, doesn't really make sense because it may not be the bottleneck. So the time you spend there is the time that didn't really help anyone. Another common mistake is using unrepresentative workloads. So you may find that your application runs just fine in the benchmark, but then it behaves very differently in real life when other services take up resources. So maybe they're sharing more cores, or maybe they're sharing the disk. In addition, if you're benchmarking with different size of data than what you would encounter in real life, you may not be able to compare it correctly. So if in our web server that is serving images, if you benchmark on 200 kilobyte images like the thumbnails because you just want to get your results as fast as possible, and in reality you serve 2 megabyte images plus in production, then you can't really reason how it's going to perform, how it translates from 200 kilobyte to 2 megabyte images, because you will be observing different effects. Now, if you run your applications for long enough, some buffers may be filling up slowly until the system grinds to a halt. So in this case, you may be tempted to fix that problem, to benchmark against it. Well, another important thing to consider here is how frequently do you restore your services? So if buffer bloat causes problems once a month or doesn't manifest itself until 3 months in, but you redeploy every week, that's not something that you should really need to worry about because it's not something that you're going to run into. So make sure to benchmark for times similar to what you're interested in production, considering your workflows as well. Now, memory pressure is another very tricky thing to account for when setting up benchmarks. If you're writing in a garbage collected language, then what you would like to do is first force a garbage collection at the beginning of the benchmark so that you don't have bad measurements due to allocation during the setup. And then at the very end, when your application is done running, you're done collecting results, you would like to force garbage collection, but this time measure it so you can approximate the memory pressure, the memory footprint of your application. And if you're benchmarking a library, then you may see that there is additional garbage collection pressure due to other parts of the system when you integrate it. There are lots of different hidden components in our systems that we may not necessarily suspect or think about immediately. For instance, you probably have a load balancer in your system, and load balancers introduce latency. They may make your long tail worse. They may hurt your throughput if incorrect load balancing strategy is used. For instance, round robin is probably one of the most common strategies that people pick for load balancing. Well, the problem is that it's subject to periodic interference and coordinated emission. And sometimes you're interested in measuring performance of one particular subsystem. But if you're interested in end-to-end measurement, then make sure you take into account your load balancer as well, because that is an essential part of the system, and it will introduce extra latencies with queuing and the time it waits at the load balancer. Now, if you're going to stake the future of your company on the benchmarking results, make sure that they're reproducible. You would like to make sure that the results are the same after you reprovision all of machines the next day. So lots of repetition, lots of confirming that what you measured wasn't just a one-off thing. Okay, so now let's talk about how to avoid some of those pitfalls. When setting up benchmarks, in my opinion, the most important thing to think about is what users' actions are. Not how we think or we would like our users to utilize our application, but how they are actually utilizing it by measuring the users' actions. And benchmarks don't really give you a magical answer like a database X is better than database Y. What they tell you is that database X is better than Y for a very particular workload Z with trade-offs and constraints A, B, and C. So what are some of the tools that we have in our toolkit to create better benchmarks? Well, one thing is profiling. profiling will tell you the frequency of calls, which functions are executed most, and which functions take most of the time, so that you can know how users are utilizing your application. Let's look at some of the profilers available out there. There are many different ones for different language platforms, for different operating systems available, so I'll only cover a few. Perf is one of them. So Perf is available on Linux systems. So Perf, what it does is it uses hardware counters to measure different events. So you may want to find out what the various basic CPU statistics are system-wide, and you could specify only measure for 10 seconds. So you would get like the cycles, number of instructions, number of cache misses. You may want to count number of system calls for the entire system and for a very particular amount of time. Or you may want to count, sample CPU stack traces, but only once every 10,000 times you have an L1 cache miss, and for a very particular time. So there are many, Perf tool is very, very powerful. It has a lot of capabilities, and it probably will do what you want it to do to measure. But it's not very easy to learn because of just pure amount of power that it has. And the output of Perf you would get is something maybe like this. So I don't expect you to be able to see all of this, but if you just run perfstat on gzipping a file, then you may get number of instructions, number of branches, number of branch misses, number of page faults, and so on, and as well as number of seconds that it took to do the operation. Another common set of tools is gprof and oprofile. Is anyone familiar with gprof, oprofile? Okay. Okay, good, one person, good. So gprof and oprofile are both sampling profiling tools. So let's talk about gprof first. So what this tool answers is, where does the application spend its time? So in order to get the data, what you'll do is you'll compile it with a particular flag, PG, so that it inserts some of the profiling code into it. And then you'll execute the code, and then you run gprof on the data that was produced during the code execution to analyze it. And it will give you something like this. So it will give you number of seconds passed. And the thing to remember here is that, so this is a sampling profiler. So what it will do is every nth, like say every 100th second, it will take a snapshot of what your system is doing, and then record where your system was, and then it will aggregate that and figure out where your system spent most of its time, and which functions were called most frequently. oprofile is somewhat similar to gprof, and the difference is in how the samples get triggered. So gprof actually uses a system call to do that, whereas oprofile uses hardware counters. So what oprofile lets you do is see a system-wide view of how your system performs, including the system calls and all the kernel stuff. Okay, so there are actually many tools out there to profile every single aspect of your system on a Linux box. And you can see some of them here. And so anything you would want to measure, there's probably a tool out there for you to dig into and figure out how it's doing in your application. Now let's talk about some tools that are available there for different languages. One of them is JVisualVM. Who here has used JVisualVM? Good. So it comes with your Oracle JDK or OpenJDK. We saw some snapshots of the heap that you can take with JVisualVM. So how heap performs over time, the size of the heap over time. As well as you're able to do thread dumps and figure out memory leaks that happen in your application and so on. There are also other profilers available to you for JVMs like YourKit and JProfiler. YourKit is actually available for free if you're for an open source project, which is pretty cool. And for the Python world, there is cprofile. I don't write Python for production systems, but I'm sure there are lots of other tools available out there. So what are other tools available besides profiling? Well, one of the common ways is to instrument your code in production. So what you would do is, right before the function executes, you would insert a timer, and then right after it executes, you will take the time that has passed, and then you will just log that in your production code. Yes, it does add some latency, but it's going to be insignificant compared to how long most of your computations take. And this combines nicely with aggregation over logs. So you're able to then retroactively go back and reason about your data and figure out how long each function took and which functions will code most frequently and so on. This approach is also similar to tracing. You may be familiar with distributed tracing system called Zipkin. Tracing basically allows you to see which machine the request came in, which machine the request was bounced around, and which functions were executed and how long they took until the response was returned back to the client. Okay, so when talking about benchmarks, we can't really avoid topic of micro benchmarks. Do a lot of people here like to write micro benchmarks to figure out which strategy they would like to use, which implementation of the code like to use? Okay, we have some, yeah. So micro benchmarks are meant to measure a very small piece of code, usually a single operation. And in my opinion, micro benchmarks are a blessing and a curse. They're quick and cheap to set up, and they answer very narrow questions very well. Like if I would like to know which sorting algorithm should I use, merge sort or quick sort, I may want to set up a micro benchmark. But they often produce misleading results. And they're not really representative of a program due to their nature because they measure a very tiny part of it. So you should put micro trust in your micro benchmark. Now, there are some common pitfalls that are specific to micro benchmarks, so let's discuss them. One of them is choosing your data set size. As we saw earlier at the graph, depending on the data set size, we may measure different latencies. So just picking one data set size will be insufficient to tell you whether this particular approach works better or not. For instance, I discovered that merge sort works better when data fits fully into L1 cache, but quick sort is better for after. Now, if you're measuring a tide loop that writes to a file, make sure you don't remove the side effects, and you measure those because they will be the ones taking most of the time. And make sure to be aware of the clock resolution. It's a visual pun. So you may discover that your clock resolution is 1 millisecond, and if you're measuring a function that takes 2.4 milliseconds, what you'll see is actually that it takes 2 milliseconds, and then 3 milliseconds, maybe 2 again, and there are statistical ways to correct for that, but it's hard to get right. And a better way to do this is to measure many iterations at once. So you'll start measuring at the 0th iteration, and then stop measuring at the nth iteration, and then divide it by the number of iterations you executed. Dead code elimination becomes a particular problem when doing benchmarks. So dead code elimination is a compiler optimization that figures out which code is no longer reachable or no longer needed and then just tosses it out. So if you're writing in a just-in-time compiled language like Java, then if you're no longer executing the rest of your program, only executing a very small part of it, then JIT will decide to toss out the rest of your program. And now you're just measuring a completely different program than what you started out with. And another thing that's good to be aware of is doing constant work per iteration. So if I'm adding some elements to a tree, and I have a tree of 3 nodes, and then the work grows slowly, logarithmically in fact, I may not be concerned about it, but the problem is that any operation on a tree of 10 nodes will be 3 times as fast as any operation on a tree of 1,000 nodes. So your work will be slowly increasing, and now you're not really comparing the same operation because your data sets will be different and you'll be experiencing different latencies. Okay, so what should a benchmark do? We talked about many different things that it shouldn't do, that we shouldn't do when we set it up. Well, benchmark should measure a behavior of the system that you're interested in. It should represent a realistic workload. It should run for sufficiently long time. And it should compare things in the same context and produce predictable and reproducible results. There are many wonderful resources out there on how to write better benchmarks. I'll make sure to post the slides, but also feel free to use the great search engine. And some of the things that I thought were interesting is, so on the bottom, the trust no one, not even performance counters. So the author actually looked into perf tool and how it attributes cycles to mfence, which is a memory fence instruction that causes all the writes to flush the buffer before continuing, and lock instruction. And what the author found is that he expected that lock instruction would take less time, but perf reported that it took much longer. And the reason for that is that the way instructions were attributed to the lock instruction got much more attribution for things that were already finishing anyway. Okay, so if you were to take out anything from this talk, I think it should be the 3 following points. It caches all the way down, and when you're benchmarking, you're probably measuring a very particular one cache level. And you would like to make sure that you understand the architecture of the application so that when you're optimizing your application, you're not optimizing for a wrong cache level. It's like in the case we saw with when we're missing instruction cache in a bloated binary. It was due to instruction cache, so no matter how much work we do for optimizing our cache server, it wouldn't really make a difference. Another one is outliers. Outliers carry much more informational density than the rest of the data that you will get that fits within your expectations. So outliers should serve you as a signal that either your application does something that we didn't understand before, or your benchmark does something incorrectly, or it's actually just that unlikely event which you will actually hit when you work at scale. I found more bugs in production code and the benchmark itself by investigating specifically the outliers. And the third one is being aware of the workload that you use when you're benchmarking. If we use the benchmark to drive this truck on normal asphalt roads and have a normal workload for the number of pounds that it could carry, then this truck would perform poorly in these road conditions with this load. You can think about it as the application running a production. So we want to make sure that workload that we optimize for when we benchmark is the same that we would expect in production. And that is it for today. So I'll take any questions you have now. Thank you. Yes, question.
Not a question, just something I just had on when we talk about the development and production requirements, and when you're doing databases, you run into something like the amount of data that you have stored in data, the structure of data, you're running into different index paths. Similar to different sizes of data, but
Right. Yeah. Sorry, is there a question as well? No. Sorry. Okay. Yes. Thank you. Yeah. So, the comment was, we saw some of that when we were benchmarking with databases, right? And when I was working on a search engine, we actually had set up so that we would duplicate the production workload, and we tried to match as closely as possible our environments, because otherwise, anything that we measure in our test environment would just be completely misleading. So we put a lot of effort into making sure our test environment is as closely matched to production, and we do similar amounts of workload in both environments before we set out to measure performance of it. Any questions? Yes?
If you weren't able to access a production environment, just the nature of the essential work, do you think it would be better to try to at least add tooling to a production environment, at least be able to get metrics back from that environment, or would you rather spend time trying to simulate a production environment?
So the question was, if you can't get access to your production environment, if you can't fully represent it and imitate it, would you rather spend more time trying to simulate it and recreate it, or would you just have some metrics that are captured in production? Is that a reasonable summarization? So I would say that measuring it in production is much more valuable because you will, even when you simulate, simulation is only an approximation of what you're actually going to be experiencing. So some things like that I talked about, like adding some code to measure and instrumenting the code in production is incredibly valuable because not only do you have the data that you can go back to and figure out whether improvements happened, but also once some artifact that goes away after the bug fix or change of environment, that's something that you're always able to go back and figure out. So capturing the production environment, in my opinion, is very valuable. Now, sometimes some people work with systems in which adding that extra latency is really not acceptable, in which case emulating the production environment will be more suitable to them. So it's a trade-off, and it depends on which domain you're in, which problem space you're in. Yeah. Any other questions? Three, two, one. No questions? Okay, thank you very much for coming. Thanks.